Here we're going to look at question 18 from section 2 of the ENGAA 2018 paper. So in this question we're given the following scenario. We have a steel ball which starts in the position shown in this diagram here, which has a height of r above this point P. Now we're told that this ball is released, and when it passes P, it goes to a maximum height again of Q. So obviously the ball has lost some energy, and we have a frictional force acting against this ball, which we're told has a constant magnitude whenever the ball is moving. So with this information, we are asked to find the kinetic energy of our ball when it initially passes the point P. If you'd like to have a go at this question yourself, please pause the video now, otherwise let's have a go at doing it. So since we've asked to try and find the kinetic energy of the ball at point P, let's try and think about the energy of the ball at some different points. So the easiest ones are probably the points at which it's stationary, its initial point, and at Q. At this point, the only energy the ball has is going to be gravitational potential energy. And what's the expression for this gravitational potential energy? Well, generally, it's that it's equal to the mass of the object multiplied by the gravitational field strength multiplied by the height of the object above our 0 point. So if we take the point P to be at 0 gravitational potential energy, then we can find the initial energy of the ball by simply substituting in the height of the ball, which is just going to be r. So the initial energy is just mgr. Next, we can try and consider the energy of the ball at the point Q. So again, since the ball is stationary, the only energy is going to be the gravitational potential energy. But for this, we need the height of the ball at Q. So let's try and think about how we could find this. If we zoom in and take a closer look at our diagram, then we know that at this height Q, then the vertical height above P can just be found by considering this distance here on our diagram. So an easier distance to find is going to be this one here, since by some basic trigonometry, and knowing that the distance of this length here is going to be r, then we know that this height is going to be r cos 45, which of course just is going to simplify to r over root 2. Therefore, just to find the height of Q above our point P, we can just take the total distance r, r over root 2 from our total distance r, giving us that the height of Q is just r minus r over root 2. So if we go back to our equation for the gravitational potential energy and substitute this value in as the height, then we get the energy at Q is just mg and then r minus r over root 2. But we can just factorise an r out to get this expression here. So now that we've got these, we can try and think about why they're important. Well, obviously the energy at Q is going to be less than the energy at the initial point. We can see that the energies are different, which is due to the frictional force acting on the ball. Now we were told in the question that the frictional force acts at a constant rate, so energy lost due to friction is going to be lost at a constant rate. So the change in energy between this is going to give us an indication of how the rate of energy change, or what the rate of energy change is. So if we do go ahead and think about the energy change, then it's just going to be mgr over root 2 by taking this value away from our initial value. Now with this information we can consider the point P. So at P, the ball has travelled 2/3 of the distance that it's going to travel to Q. Now we know this because Q is at an angle of 45 degrees from the vertical, so it's just going to be half of the way up here, so this is going to be like a quarter of the semicircular distance if you like, and this is the other half. So the whole distance here is 3/4 of our semicircular distance, and therefore at this point we're 2/3 of the way to Q. And now since we were told that friction acts at a constant magnitude, we know that the energy change is going to be 2/3 of the energy change at Q. So multiplying our energy change by 2/3, we get this expression here. So if we know that this is the energy lost at point P, then we know that the energy at the point is going to be the initial energy, take away this energy change, where all I've done here is just divide by r root 2 to get the energy change is root 2 over 3 mgr, and then simplifying this by just factorising out our mgr, we get that the energy at P is just mgr multiplied by 1 minus root 2 over 3. Since there's no potential energy at this point, then this total energy is just equal to the kinetic energy of our ball. So this answer corresponds to answer B, given in the question.